All right. So this problem says how much ammonia. Now remember, ammonia is NH3. That's this guy's name. Is produced when you add 35 grams of nitrogen. So I give you nitrogen. And then and 4.20 grams of hydrogen. So let's go back over. So I'm trying to find this guy, and I give you nitrogen and hydrogen. So let's go back over why you know this is a limiting reactant problem. The way you know is I gave you numbers for both reactants. So in order to figure out how to calculate the ammonia, we have to decide which one of these we're going to use to calculate the ammonia. Once we decide which one of these we can use, it's just basic stoichiometry. But this is a little bit harder first step. So 35 grams of nitrogen. Now, in order to do this, you have to be in moles. So first thing you should do is balance the reaction. This reaction isn't balanced, so you want to balance it. So I need 2 nitrogens, so I'll put a 2 here because there's 2 right here. Now I have 6 hydrogens, so I put a 3 here. And now this is balanced. Okay, so 35 grams of nitrogen. So I write 35 grams of nitrogen. And I have to turn nitrogen into moles. So you go to the periodic table and you find nitrogen. Nitrogen is 14.01 grams per mole, but there's 2 of them in N2. So it's 28.02 grams per 1 mole. That would give me my moles of nitrogen. Now over here, I'm going to do the hydrogen. I'm going to just try to do it in a different color so that we don't mix them up. Of course. Okay, I give up. Okay, so hydrogen. 4.20 grams of hydrogen is given in the problem. And you have to turn grams to moles because the ratios that these react in are mole to mole ratio. They aren't gram to gram ratio. So we can't compare grams. We can only compare moles. So hydrogen is 1.01, but there's 2 of them. So it's 2.02 grams per 1 mole. And let's take a second to calculate these 2 numbers out. Now, I'm not finished with the problem, so I'm going to write out a handful of digits. Okay, now you have to be careful because you can't right now just look at this and say, oh, nitrogen is smaller, is less than this number, so it's my limiting. You have to consider mole ratios. You cannot compare them until you've considered mole ratios. So at the end of class, I taught you a cheating method of how to do this quicker. Do you remember what it was? So usually you could do this and do mole to mole to ammonia and figure out who's smaller and it's your limiting. That way works. Or you can take and divide by the respective coefficient. That is the same as doing mole to mole ratios, just like in a more simplistic way. So what I mean by that is there's an invisible 1 in front of the nitrogen, right? So you would divide nitrogen's number by 1 because there's a 1 in front of it. This is like doing stoichiometry in a simplified way. And then hydrogen is a what in front of it? A 3. So you would divide it by 3 because it's going to be a 3 to 2 ratio. Why does the 2 not matter if you were to do it the long way? Well, because they're both going to a 2. So it's just what their number is that matters because the top number is going to be 2 for both of them because they're both going to ammonia. So that's why this is like a cheating method. Okay, and I'll show you the long way in just a second. Now you can compare them. So 1.249 divided by 1 is 1.249. 2.09 or 2.0792 divided by 3 is 0.693. That number is smaller, right? So this is my limiting reactant. I'm going to circle it. Now, I would like to show you the long way and show you that in essence, you're doing the same thing. I am happy for you to do it whatever way you feel the most comfortable with. So I'm going to start over again. 35.0 grams of nitrogen. You take nitrogen and turn it into moles because you cannot compare them unless you're in moles. And then you use the nitrogen to go to your product. For every 1 mole of nitrogen that react, 2 moles of ammonia are produced. How did I get that? From my balanced chemical reaction. This is a 1-to-2 ratio. So this number in moles comes out to be 2.50 pretty much, moles-ish, okay? And then you do it again for the hydrogen, just like we were doing up here, 4.20 grams of hydrogen. And hydrogen is 2.02 grams per 1 mole of hydrogen. And then for every 3 moles of hydrogen, 2 moles of ammonia are being produced. So this is what I'm saying. We took this and then we divided it in our shortcut way by 1. We ignored the 2, right? We took this and we divided it by 3. We ignored the 2 because the 2 is the same in both ones. So it technically doesn't matter. That's why I call it a shortcut way. This is a little bit longer, but it works also. So if you feel more comfortable and you understand this better, I'm totally fine if you do this way. So 4.2 divided by 2.02 divided by 3 times 2. This number comes out to be 1.386 something moles. This number is smaller, so this is my limiting. Both methods work. So you do whichever one you feel most comfortable with. Whoops. So they didn't ask for moles though, right? They asked for grams. So to find the grams, who are we going to use of ammonia? We're going to use hydrogen. Why? It's my limiting reactant, so it's going to run out first. So you kind of take this thing and you keep extending it. So 4.20 grams of hydrogen, 2.02 grams of hydrogen for every 1 mole of hydrogen. 1 mole of, 3 moles of hydrogen that react make 2 moles of ammonia. So basically, I'm completely ignoring nitrogen right now. It's not relevant because it's not going to run out. And then, 1 mole, 2 moles of ammonia. And then 1 mole of ammonia. So a nitrogen is 14 and hydrogens are 1 each. So this is like 17.04 grams if you add them together. And this will give you the mass of ammonia. Now, look, some kids like doing this way better because you almost already get there. So you could go all the way out to grams on each of these and instantly have grams, and whoever is the smallest grams also determines your limiting, and now you're already in grams. So that way works also. What I mean by that is instead of stopping at moles, which is okay to stop with, you can take these all the way out to grams. For both of them. And I'll do this just to show you the other way. So 35 divided by 28.02 times 2 times 17.04, we get, this is 42.6-ish grams. This is 4.2 divided by 2.02 divided by 3 times 2 times 17.04, and this is 23.6 grams. So look, this produced less, so this is my limiting. So you could do all the work up front to figure out the limiting, and at the same time you can figure out the answer, the mass, okay? Whatever you prefer. So the number is 23.6, so 23.6 grams of ammonia is produced. Now, let's have a flashback to law of conservation of mass. Oops. at the beginning, of this reaction, you have your reactants. So if you look back, that's 35 grams of nitrogen and 4.20 grams of hydrogen. This is before the reaction starts. So no product yet because the reaction hasn't started yet. So what does this add up to? 39.2 grams total. Okay. When the reaction's over, we have just now made 23.6 grams of ammonia, 0 grams of hydrogen should be left because it runs out. That's the whole point of it being limiting. It runs out and nothing, then the reaction stops. Like nothing has anything, the nitrogen has doesn't have a buddy to react with. So everything else just hangs out after that. So until it ran out, we were able to make this much ammonia. This guy runs out and now we should have some excess, some leftover nitrogen. So now how do we figure out how to do the excess? So I'm like running out of room. I'm going to do the excess down here. So just as we said before, the limiting reactant determines everything about the chemical reaction. So every time you do math, you will always start with the limiting reactant. Always. So who's my limiting reactant? It's hydrogen. So I'm going to start with my limiting reactant, 4.20 grams of hydrogen. And I have to turn it into moles, as always. 2.02 grams of hydrogen for every 1 mole of hydrogen. Now, instead of going from jumping, so once we found the limiting reactant, we jumped over to the ammonia using mole to mole ratios to figure out how much we were going to make. Well, the same thing is true for the excess. You just jump from the hydrogen over to the excess now instead. So for every 3 moles of hydrogen that react, 1 mole of nitrogen will react. And 1 mole of nitrogen is 28.02 grams. Nitrogen is 14.01, and there's 2 of them, so you add them together. Now, be careful. This part right here, I said for every 3 moles of hydrogen that react, 1 mole of nitrogen will react, meaning this number that comes out is how much reacted. That is not the excess. It is reacted. This number is reacted because the stoichiometry right here is based on them reacting. So you find out this number, 4.2 divided by 2.02 divided by 3 times 28.02. And this number is 0.4 grams-ish. It's 19.419802 reacted. So how do you get excess? Well, we know that there were 35 grams of nitrogen at the beginning. So if there was 35 grams of nitrogen and 19.4 of it reacted, that means you lost 19.4 of it. This is a subtraction problem. The difference between the starting amount given in the problem, you had 35 grams to begin with, and what we got using our stoichiometry is your excess. So 35 minus 19.4 leaves us with 15.6 grams of nitrogen unreacted, excess, left over. So
that makes sense now, because like the last time I did this, I was confused. Like, why is there extra of this?
Does that help?
Yeah, this actually does help. This
Okay,
clarifies more stuff.
Good, I'm glad we're doing it together then. That's why this is harder, so I wanted to spend another day on it, and then I'm going to let you practice on your own. So at the end, we made some ammonia. The hydrogen was all used up. It's all gone. But we have some leftover unreacted nitrogen. How much? 15.6 grams, right? So how much stuff do we have at the end? 6 plus 6 is 12. You put a 1 up here. 5, 3, 8, 9. 39.2 grams at the end. You had 39 grams at the beginning, and you have 39 grams at the end. This is the law of conservation of mass. Yes, stuff changed, stuff got used, stuff reacted, but you can't just have mass appear and disappear out of nowhere. It can get converted and changed into other stuff, but it doesn't like disappear or appear. So like if for some reason I don't always make you like check your law of conservation of mass, but if you do and it's off, it's because one of your numbers is off, most likely, okay? So the last part of this problem is percent yield. So it says if only 15 grams of ammonia were made in the lab. So this is your experimental. When they tell you you've made it in the lab, it means you've done the experiment. So you take experimental, 15 grams, that was given in the word problem, divided by theoretical. That's the number you calculated. This number is like perfect world scenario, doing the math, what you should get theoretically. So this isn't as good of a lab. And then you multiply by 100 to turn it into a percent. Oops. Jeez. I cannot type in my calculator. 63.6% yield. I mean, not the worst, but not the greatest. So definitely a lot of error when whoever did this lab did it. They were supposed to get 23.6 grams of ammonia out, and they only got 15. Okay. So because I skipped how to do the excess in the prior problem, and that seems to be a harder one to do, let's do that one also this time. Now, what I'm going to go back to is this law of conservation of mass again. And in this problem, we already did most of it. So we had 2.5, so oops. So to start, and at the end, we had 2.53 grams of sodium in this problem and 2.53 grams of chlorine. So what's that? 6, 0, 5. So you had 5.06 grams of stuff at the beginning of the reaction. If you look back on this problem, what were we making? Sodium chloride. So the amount of sodium chloride we made, we did all this math, right, was 4.17 grams of sodium chloride was made. Okay. Now, I don't remember. Can someone tell me who my limiting reactant was? I don't remember. Was it the sodium or the chlorine? It was the chlorine. Okay. So we shouldn't have any chlorine at the end. It should have run out. No grams of it. All right. Which makes my sodium my excess, meaning there's going to be some sodium left over in there. So how do we figure out how much sodium? Well, we start with the limiting reactant every time. So my limiting reactant was chlorine, so I will use chlorine to start this problem. All right, so here we go. 2.53 grams of chlorine, because it's my limiting reactant. Chlorine's molar mass is 70.9. 35.45 plus 35.45 is 70.9 grams per 1 mole of chlorine. Now, instead of jumping from chlorine to sodium chloride, which is what I did the first time, I'm going to just jump to my excess instead. I will do my mole ratio from my limiting to my excess. So for every 1 mole of chlorine that react, 2 moles of sodium react. And 1 mole of sodium, and you go to the periodic table, is 22.99 grams. So do not forget, when you calculate this out, this number is how much reacted. So it looks like 1.64 grams of sodium reacted before the chlorine ran out. So we had 2.53 grams of sodium to start the reaction. That's how much we had initially. So if this is how much was lost or consumed or used or reacted, those all mean the same thing. The subtraction of these two numbers is what gets us what's left over. It's like me saying I give you $2.53 and then I take back $1.64. How much do you have left? It's the same concept, but with chemicals and not money. So it looks like there's hold on, let me move this so there's no confusion. So 0.89 grams left over, also known as excess. So if we go back to this is how many grams are left over, and we add these two numbers together, 4.17 of sodium chloride was produced once the reaction stopped. No more, oops, I'm sorry, this is Cl2. No more chlorine was left because it was the limiting reactant and it ran out. And we have some leftover sodium sitting in there unreacted. And you add these up and guess what you get? Law of conservation of mass. The mass is the same at the beginning as it is at the end. We got some new stuff out of it and we lost some stuff and we have some leftover stuff. So stuff was rearranged, flipped around, moved, which is fine. But you can't just have stuff appear or disappear. So these masses match.